Hey, Hunter, how you doing? Isn't it great to be back in session? Here I am in all my glory. We're going to turn to page 504 and get out your homework. You remember I gave you 4 problems from page 523. So if you don't have your homework out, you might want to go ahead and pause this thing and go get it. Good, you're back now. So let me tell you what you need every day. You need a pencil, a paper, a packet, if I have one. After this chapter, we won't have one. A book and a calculator. Now, after every day's lesson, which should be around 15 minutes, I'm going to go ahead and give you some homework, which are called testlets. That's a new word for my vocabulary. And they will be open notes, open book. Please do your homework correctly by yourself and completely, and then check with others to see whether or not you got it right. But don't just check with other people blindly ahead of time. Now, there's still a chance that I might have you do handwritten homework assignments, but these will be multiple choice, true, false, matching format, just like a test. And if I do ask you to send in your notes, just to let me know that you're actually taking notes and paying attention, that'll be fine too. But primarily, I'll just be doing these little testlets, maybe half a dozen questions after every lesson or so. And so you get 3 cuts the remainder of the 9 weeks so that you can goof up on a couple of them. Like, say, the first one and the second one, that's what they don't want us to grade, but I'm going to go ahead and do that anyway, and I'll give you cut grades. Same thing as not grading it. That way, maybe later on, if you get a good grade now, you can just take those cut grades later. Okay, so number 7 in your homework was 3,561 joules. Number 8, 569 Kelvin. Number 9, 2.06 joules per gram Kelvin. And 10 is 0.23 joules per gram Kelvin. Now let's go back to the page I mentioned before, page 504. We have a formula there for enthalpy. Mr. Schultz, would you read the definition for enthalpy change? Sure. An enthalpy change is the amount of energy absorbed by a system as heat during a process at constant pressure. Now, when it talks about constant temperature or constant pressure in chemical reactions, it's talking about at the beginning of the reaction, it's the same as at the end. Now, during the reaction, the temperature might go up, but they bring it back down to what it was at the beginning. That's just what they mean by that. And incidentally, you remember STP was temperature of 0 Celsius? Well, now that we're in thermochemistry, the standard temperature is 25 degrees Celsius, not 0. And so the enthalpy formula goes like this. H is products minus reactants. If you please, H can be referred to as heat. Why don't they call it heat? Why do they call it enthalpy? I have no foggy idea. Somebody just decided to do that. So the enthalpy of reaction on page 505, follow along, is the quantity of energy transferred as heat during a chemical reaction. It's called the heat of reaction. So we have this thing going on right here. It's called an electrolysis. You remember that in the front of the room. I have this much hydrogen right now, that much. And that measures out to be about 29 milliliters of hydrogen. And of course, I've got to pop that because you all enjoy that. So here we go. I'm going to take a wood burning splint, try not to burn down the house. I'll go ahead and wish I had an accomplice, but I only have 2 hands, so you forgive me here. I'm going to go ahead and gather up some hydrogen. And then I'm going to pop it. Whoa, that was pretty good, wasn't it? Now that was 29 milliliters of, I hope I don't set off the smoke alarm, 29 milliliters of hydrogen. Question is, how much energy was released? Now, a lot of sound was released, but how much heat was released? Well, we got to start out with the equation. Hydrogen oxidized and produced water. Water gas, water vapor. Hydrogen gas, oxygen gas, produced water gas. But as soon as it was produced as a gas, you can see the cloud on the inside of this. Those are water droplets. It converted into liquid water, and it released some more heat, because you know that when the vapor is condensed, you've got that heat of vaporization that is released. Okay, but we're talking about the heat that was produced from a chemical reaction. You see, when we had wild and active and crazy hydrogen and wild and active crazy oxygen, when they combine as a chemical compound, they slow down and they release energy. And so how much is that? Well, they've had experiments. On page 505, you're going to see that it's going to release about 483.6 kilojoules of energy. So this is a product plus 483.6 kilojoules of energy. So what is that? That's delta H. That's the heat of reaction. Now, that's for a balanced equation. That's for 2, 1, 2. So 2 moles of hydrogen produces 2 moles of water vapor, or some fraction of 2 moles. But if you have that's the proportion, but if you have 2 moles of that, it'll clearly release that much energy. If you had 1 mole, it would create half as much. In fact, let's go ahead and take 1 mole. Divide everything in half. Can you do that? Yes. In thermal chemistry, you can do that. You can have fractions as coefficients. Okay. So now what we have is 1 mole of hydrogen plus 1/2 mole of oxygen produces 1 mole of water vapor. And we'll cut that in half, because it only releases 1/2 as much energy. And the answer to that would be 241.8 kilojoules of energy. Now, there's 2 ways to write a thermochemical equation. Thermal meaning heat, and chemical meaning chemistry, of course. One way is like that, and the other way is like this. So 2H2 plus O2 yields 2H2O gas. And instead of making this a product, we will say the change in enthalpy during that equation is negative 483.6 kilojoules. And that is 2 moles worth of energy. And it's listed as a negative. Well, why is it a positive up there and a negative down there? Well, when you wrote it as a positive, it means it's releasing that much energy. But in chemistry, when energy is released, we give it a negative sign, so it's not part of the thermal, it's not part of the equation. Up here it is. And so if it's not part of the equation, it's written afterwards, it says that the amount of heat released is that much for 2 moles of water vapor. So it's a negative when it's written separately from the equation, and it's a positive if it's added onto the equation. Now that's for an exothermic. X means to release or go out. Exothermic equations release energy, and it's a negative kilojoules of energy. Endothermic is just the opposite. You got to put heat in or some form of energy. And in the case of what we have going on right now, we're putting electrical energy in there and cutting the water in half. And that's endothermic. And it works the same way, except the sign is different. The balanced chemical equation looks like this. We're going to take water and we're going to break it into hydrogen and oxygen. And we're going to say, instead of releasing 483.6 kilojoules, we got to take in 483.6 kilojoules. So it's added as a reactant to the thermochemical equation. Or you don't need to do that. You could go ahead and instead say delta H is 483.6. And that is, instead of negative, it's going to be positive. It has to be taken in, kilojoules. And it's written separately from the thermochemical equation. Okay, now, how many milliliters did I say I removed from there? 29. I think that's what I said. What we're going to do is, I'm going to calculate how much energy that would be. Heat energy. By using this thing called the ideal gas law. And the ideal gas law goes PV equals nRT. The pressure in my house right now is about 1 atmosphere. The volume of that gas, the hydrogen gas, was 0.029, 29 milliliters, 0.029 liters. We're going to calculate the number of moles that that would represent. R is 0.082, and the temperature is about room temperature, 25 degrees, about standard. And so 25 plus 273 converted into Kelvin is 298. So let's go ahead and take our calculators. And let's take 0.029 divided by 0.082, further divided by 298. And you're going to get 0.0012. Moles of hydrogen gas. But the equation calls for 2 moles. So the question is, when that popped and released energy, did it really release 483.6 kilojoules? Or did it release only a fraction of it? Because we only had a fraction of 2 moles. Well, we did. We only had a fraction of 2 moles. So how much heat did it release? Well, let's see. 2 moles is to 483.6 as 0.0012 moles would be to X. And so we're going to take that times that and divide it by 2. And be a very small number of kilojoules, thousands of joules of energy. Now take your book And look on page R66. If you go all the way to the back to R66, you're going to find enthalpy of formation. What was the compound that we formed? Wasn't it water vapor? But as soon as it forms water vapor, it condenses on the inside of this test tube. Let's look at water vapor. It's called hydrogen oxide on this table. And look at it as a gas. Do you see negative 241.8? Negative meaning it's being released when this compound forms. And it's 241.8, which is exactly half of that, because what does it say at the top of this table? It says, no, not at the top, at the very bottom. At the very bottom, it says, all values of delta H of formation are expressed as kilojoules per mole at 25 degrees Celsius standard condition. So kilojoules per what? Per 1 mole. What does this equation call for? 2 moles. So it's half of that. The tabulated value is half of that, or 285.8. Now, when it turns into a liquid at the same time, it releases 240, negative 241.8, and then it releases 285.8 after condensation occurs. So it releases about 44 kilojoules because of condensation. So this table we'll refer to quite a bit when we're talking about putting elements together to make compounds. It's called enthalpy of formation. See ya.